Okay, here's part 2 of my lecture on electric fields. I'll take you through the basic mathematics of electric fields. So first of all, recall Coulomb's law from the previous lessons. So let's say that I have two charges here, Q1 and Q2, and they're separated here by a distance R. Okay, and then the magnitude of the electric force that occurs between the two charges is governed by Coulomb's law. It's this expression here. Okay, now let's say specifically that I'm going to be talking about the force on Q2 due to Q1. So let me label that here. Force on Q2 due to Q1. In other words, the electric field associated with Q1 is exerting force on Q2. So how would I then just describe the electric field associated with Q1? Well, what I would do is take this expression here and just divide out by the charge Q2. That then gives me the following. So the electric field due to Q1 is equal to this force equation, the force on Q2 due to Q1, but then we would just divide out by the Q2. This is the same thing as me earlier taking the marker and dividing out by its mass, if you recall, to describe the Earth's gravitational field. Here we're describing the electric field due to Q1. So it's the force on Q2 due to Q1, and then we just divide out by the charge Q2. This then means that the electric field due to Q1 is this expression right here, but we just remove the charge Q2. So E due to Q1 is KQ1 over distance R squared. Okay, now the units associated with the electric field come from this expression right here. It's in terms of newtons per coulomb. Like so. And now I'm just going to take a look at two lecture examples of the use of these basic expressions to give you the idea. The first of the two examples deals with a situation like this. So at this point, go ahead and pause the film and then copy down that first example into your notes, and I'll run through the solution. I'm going to put it up on my screen to refer to. All right, so I'm going to use the same diagram here to illustrate this example. Okay, it says that we have two fixed charges that are nailed in place, they can't move. Okay, the first one here, Q1, that's equal to negative 3 microcoulombs, negative 3 times 10 to the minus 6 coulombs. The second one, Q2, that's given to us as positive 1, that's 1 times 10 to the minus 6 coulombs, positive 1 microcoulomb. And then we place them a distance of 10 centimeters apart. In terms of meters, that distance is 0.1 meters. So part A of the example says, what electric field does each produce at the site of the other? So let's break part A into two parts. Okay, so let's take a look at Q1. And then we have some point in space where Q2 is. Generically, we refer to this point in space as point P. Okay, so right here is point P, and it's a distance R away. Okay, because Q1 is negatively charged, this then means that the electric field at point P due to Q1 is going to point in this direction. We'll think of that direction, of course, as negative. So how do we now calculate that electric field? Well, we calculate the electric field due to Q1 by using Coulomb's law and then just divide out by the Q2 as I did a few minutes ago. So it's KQ1 divided by R squared, and now we just calculate and we end up with a number here in terms of newtons per coulomb. Okay, now remember the constant K from previous lectures, 9 times 10 to the 9th Newton meter squared per coulomb squared. All right, so 9 times 10 to the 9th for K, and then times Q1, which is negative 3 times 10 to the minus 6. And then divide by the distance, 0.1 squared. Okay, and when I do this process here, 1, 2, 3, 4, 5, 6, this is negative 2.7 times 10 to the 6th. So yeah, that's in terms of millions newtons per coulomb. Okay, and now we'll continue part A by doing now the problem a little bit backwards. Now what we'll do is we'll find the electric field at this point due to the charge Q2 up on the top board. So then therefore, let me do that on my sideboard over here in the following manner. All right, so right here is Q2, and now our point in space is over here where Q1 was. Okay, once again, this distance here is R. Now Q2 is a positive charge. So then therefore, at this point in space, away from this positive charge will be its electric field. Like so. Okay, once again, we'll think of that as a negative number. The reason why is because it's going to be in the negative direction. So then therefore, I can calculate that electric field in the following way. It's going to be K Q2 over R squared. So in other words, it's the electric field due to Q2, so it's equal to Coulomb's law, the force on Q1 due to Q2, and then we divide out by the Q1. That's the expression there, but it does point to the left-hand side, so then therefore I'm going to make it negative for that reason. Okay, so let me go ahead now and calculate here. So I have K, 9 times 10 to the 9th, and then I'll multiply that by Q2 up on the top board as 1 times 10 to the minus 6. And then I'll divide by the distance squared, 0.1 squared. Okay, and this comes out to be 1, 2, 3, 4, 5. This is negative 9 times 10 to the 5th newtons per coulomb. Like so. Okay, and now that I've calculated the electric fields at the various points in space due to each charge, now we'll find in part B, what force does each charge exert upon the other? Those value of the forces should be the same, but in opposite directions, and the reason why is because it's Newton's third law. For every action, there's an equal and opposite reaction, so the force that each charge exerts upon the other should be the same value, but just in the opposite directions. So then therefore, now let me go ahead and change here on the board this description now to part B, and now let's go ahead and use this diagram. What we'll now do is we'll put our charge here, Q2. So then therefore, the force on Q2 due to Q1 is equal to the charge Q2 multiplied by this electric field. The electric field due to Q1. So then therefore, it's this quantity here multiplied by Q2. So I'll just take my number here, negative 2.7 times 10 to the 6th, and multiply it by Q2, which was 1 times 10 to the minus 6. So negative 2.7 times 10 to the 6 multiplied by 1 times 10 to the minus 6, and this works out to be negative 2.7 newtons. Once again, a force here is in terms of newtons. Okay, that force that's exerted upon Q2, well, Q2 is positively charged and Q1 is negatively charged. So then therefore the force on Q2 due to Q1 is going to be in this direction, in the negative direction. Okay, now let's jump back over to here. Now what we're going to do is we'll place our charge Q1 here, and now we're going to describe the force that's exerted upon Q1 due to Q2. Okay, in this case, that force is going to be to the right-hand side, and the reason why is recall that Q1 is negatively charged and Q2 is positively charged. So then therefore there's going to be a force of attraction in this direction like so. That's to the right-hand side, that's going to be a positive number. In this case over here, the force in the opposite direction was negative. So then therefore I should end up with a positive 2.7 newtons. So now what I do is I find the force on Q1 due to Q2, and that's going to equal then this number here. We'll make it positive, however, and then we'll multiply it then by our Q1. Actually, no, I don't even have to make it positive. The negative sign there will cancel with the negative sign for Q1, and then therefore that's going to be a positive number to the right-hand side. Now mathematically, this is equal to Q1 times the electric field due to Q2. This right here is the electric field due to Q2. If you need to pause a little bit and make these adjustments in your notes, by all means do so. Okay, so now negative 9 times 10 to the 5th, and then multiply that by Q1, which was negative 3 times 10 to the minus 6. And then sure enough, I end up with, and I'll put a plus sign here for emphasis, positive 2.7 newtons. So each object, each charge exerts an equal amount of force upon the other charge, and yes, they are in opposite directions, okay? Okay, and then my second example here is to find the net electric field at some point in space due to a dipole configuration. Recall the importance of a dipole electric field. Here's a basic calculation associated with that. It's number 2 in the lecture examples. Okay, let me do some erasing here. Okay, so here's our dipole configuration. First of all, we define some axes, like so. We put the negative charge here, the positive charge here. This distance here is referred to as A. This distance here is referred to as A. Okay, and then in this direction, like so, along my y-axis, if you will, right here is our point P in space, where this distance right here is referred to as R. So just at that point, all that we're going to do is write an expression for the net electric field. This is the electric field due to the positive charge at that location, plus the electric field due to the negative charge at that location. After I calculate this, and we'll just do it in symbol form, so no numbers associated with this problem, just in terms of these distances and these charges. After that, then I'll reference once again the dipole electric field that I drew out earlier. Okay, what I have to do here is essentially just 2 calculations. So let's find the electric field here at point P in space due to this positive charge. This charge right here is some distance away from point P. Notice that distance is just simply R minus the distance A. All right, so the first portion of the electric field calculation is going to be K times Q, and then divided by that distance R minus A squared. Once again, K times this Q here, and then divide by this distance squared. Okay, and then I'm going to add to it then the electric field at this point in space due to this negative charge down here. However, the distance that this negative charge is from point P in space is R plus the distance A. However, this Q is a negative. So watch this. We'll write it as plus K times a minus Q, and then over R plus A squared. Like so. Now we can simplify this a little bit. So, and I can also factor out a KQ from each term. Minus, excuse me. Like so. And if we actually had numbers in this problem, what we would find is that the electric field at point P in space would be a positive number. What that then means is that the electric field at that point would point in the positive y direction. So in reference to the electric field dipole configuration that I drew out earlier, here's essentially what we found. Okay, so right here is the positive side of the dipole. Right here is the negative side of the dipole. And then here's what I drew earlier. Like so. But what about along this line? What about along this line? This I did not draw earlier. Well, what we just found on the top board is when we're directly above the dipole, if you will, on this diagram that I'm tracing out here, right here, say at point P, the electric field at point P points in that direction, like so. If we did this calculation for down here instead, if we had our point P down here, what we would find at that point there is that the electric field points in this direction, like so. So I'm just kind of completing the dipole diagram here, if you will, by running through this example. Okay, you can see directly this field configuration, in the little applet screencast that I've posted for you, as well as the link. Okay, that's as far as we'll go mathematically here in these types of examples in calculating electric fields. Should you enroll eventually, for example, in AP Physics C, perhaps as a senior, then you would go through all the gory mathematics as to how you calculate this for various charge configurations involving some calculus, which of course is what we're skipping here. Okay, so that concludes part 2 of today's lecture. Make sure that you follow the directions for uploading your notes.